In this lecture, we will study a Dirac-Delta function. It is a brief primer on Dirac-Delta function. Let us understand this from a physical point of view. So, therefore, we consider a Q charge is distributed over a length L. Then what will be the linear charge density? It is nothing but lambda equals to Q by L. It is already known to you from the basic electrostatics course, and it is depicted in the figure A. That is length L. It is a one-dimensional x-axis supposed to be, and over length L, Q charge is distributed uniformly. That is the main point. And what will be the charge density? That is already known, lambda equals to Q by L, and it is shown graphically in the figure B. So it is the line charge density lambda, and it is the x-axis. Here the line charge density is Q by L, and it goes up to L distance, and it becomes 0. So that is a kind of box kind of thing, and the central point is supposed to be the x0. And this can be, the charge density can be written in this form: lambda x equals to 0 if x is less than x0 minus L by 2, halfway distance, and Q over L, that is if x0 minus L by 2 to x0 plus L by 2, where x belongs to in this range, and it is 0 when x is greater than x0 plus L by 2. Now imagine the situation where length of the line segment is squeezed to L by 2. That means we are squeezing the length element over which the charge is distributed. There is no charge, there is no change of, in this case there is no change of midpoint and the total charge Q. Now lambda becomes, lambda equals to Q, and hence it goes to L by 2, and Q comes out for the sake of convenience 0, 2 by L 0, and along with the redefinition of the length over which the charge is distributed, here x0 minus L by 4 and x0 plus L by 4, over the length is L by 2. In this way, if we shrink the lines segment to L by n, then the line charge density can be written as Q times 0 whenever the length is x is belongs to x0 by L by 2n, and n by L when it goes when the x belongs to x0 minus L by 2n to x0 minus L by 2n, and that should be, I am sorry, and that should be the plus x0 plus L by 2n, and 0 whenever x is greater than x0 plus L by 2n. So if we represent this pictorially, that means whenever it is distributed over L, this is something like a box. Whenever it is L by 2, the box is getting squeezed in the sideways, and the height of the box is getting higher. And if it is in this way successively, you can say goes on, the width of the lambda width of the charge distribution lambda decreases and height increases. Overall, the charge is distributed within that length element. There are many functions that describe this kind of distribution. This is a kind of distribution, I think you know, a kind of distribution. And if we interpret this as, if we integrate this as minus infinity to plus infinity lambda x dx, that is equals to Q, it always gives you the total charge. It is convenient to define in this way. It is defined as delta n. It is a sequence of function. In delta n x lambda n by Q, it is generalized. So in this case, you always remember that minus infinity to plus infinity, you integrate the whole length scale x element, delta x axis rather, delta nx dx, that must be 1. integer over the all real number is 1 and it is independent of n. Definitely. There are many situations in physics, natural sciences and engineering. A quantity is 0 everywhere except at a single point or near a single point, and it is infinite at that point. It is a very higher value. That means in such a way that its integral over the any interval containing that point has some finite value. That is, formally the Dirac-Delta function is defined as delta x equals to 0 when x not equals to 0, and fx delta x dx must be the f naught, where fx is the well-behaved function and integration includes the origin. This is the way to define formally, more or less. It is a formal definition. A Dirac-Delta function, in a physicist way of defining Dirac-Delta function, rather includes the origin. There are no such function. The above properties obey this kind of properties, and it may be approximated by sequences of function. It is sequences of function tending to that kind of behavior. For example, delta x equals to n over root pi exponential minus n square x square. This kind of behavior where the function reaches the maximum value, that means n by pi, smoothly, and it goes decreases to a zero value, almost zero value, asymptotically reaches the zero value as the function increases. So there is some x naught, x equals to that means what I want to say, at x not equals to 0 it reaches the maximum value. That means is a blowing kind of thing, that it goes to higher value at x not equals to 0, and away from x naught in the both side of the axis it becomes 0. This kind of behavior mimics this kind of behavior whatever we have thought in our charge line charge density example, and it is that kind of example in a redefined form. This is a kind of box function, and box is increasing its height and decreases weight, and there is a Lorentzian kind of thing. This is a Lorentz function. This also behaves similarly. My home task, this is my home task. You plot this and study the behavior with where the n is increasing. And there is another thing, that is sin x by pi x. This also has the same kind of behavior. You plot this, I will come to this, and 1 over 2 pi minus n to n, and e to the power I x t dt, and that should be n goes to when n goes to infinity, then it's something like a behavior of a delta function. I will study this function particularly in connection with Fourier transformation. That is very much important. And all these sequences obey the properties of the Dirac-Delta function. These are that means minus infinity to plus infinity, delta x, that is very crucial thing. Delta x fx dx must be, and delta n should be higher, n should be large. Limit n tends to infinity, delta nx. It is sequence of function. Delta function is always represented as sequences of function, or rather a distribution, so to say. There is no mathematical function in a truest sense of the term. Delta nx fx dx. So delta x is labeled as distribution kind of thing, whatever I have said earlier. Some properties of delta function, I am not going to prove this. Delta x equals to minus delta minus x, delta x, that is equals to delta minus x. You try to prove this, and it is standard thing. And delta ax must be 1 over mod of a delta x. This also a property. And delta x minus x naught, it is shifted to x naught, and fx dx must assume the value of the function at x naught, and derivative of the Fourier delta function gives you the where fx is a well-being function, a product of this gives you minus f prime, that means the first derivative with respect to x naught. And there is another property, if argument of the delta function is a function with simple zeros at points ai on the real axis, then this property is very much holds by the delta function. Let us consider the representation delta x equals to 1 over 2 pi minus infinity to plus infinity to the power I k x dx. This is a zeroth equation. Above integral is an improper integral and do not absolutely converge, definitely. And we write this equation 0 as delta x equals to 1 over 2 pi. I am writing in this way, limit n tends to infinity minus n to n e to the power I k x dx. Limit n tends to infinity, and if you integrate this, it gives you I in x minus e to the power minus I in x, and 1 by 2 pi ix is there, and that is the denominator, and that is the thing. And so delta x equals to limit n tends to infinity, and what is that? Basically sine nx by, and there is a, if you know the e to the power I theta and e to the power minus I theta rules, and if you sum this, so rather subtract this, and you will get sine nx, and 2 is going out, and it gives you basically I is going out, so pi x. This is the basically whatever this function represent, and if we write this in this form, that is sine nx by pi x. And we know if x tends to 0, sine nx by nx is 1, but here limit n tends to infinity sine nx by pi x assumes a large value whenever x goes to 0. And we try to understand from the graphical point of view. I have plotted this function sine nx by pi x for different values of n equals to 1, n equals to 2, I think n equals to 3 or 4, and in a successive manner I have plotted in GNU plot, and it shows the function is getting squeezed in the lengthwise, and height is increasing, and it supposed to be for n equals to 2, I think 0.35, and then for higher value of n it becomes 0.7 and 1, and if you increase the n indefinitely, it will assumes a large value. Apart from that, as the function is going away from x equals to 0 value, it becomes negligible contribution, and the contribution to that function is very much less, and there is a negative and positive values are also there, and a function oscillates with smaller amplitude with negligible contribution. Try this representation. What happens whenever delta x dx is integrated over minus infinity to plus infinity? So therefore we put minus infinity to plus infinity integration limit n tends to infinity sine nx by pi x dx. As we know, somehow integration minus infinity to plus infinity sine nx by x dx is pi. So therefore here is a pi, and whole integration is pi. That means it gives you 1. So our representation obeys the very basic properties of the delta function. Indeed, delta some nx, because it is a distribution kind of thing, I should put a n delta suffix n here. So sine nx by pi x, or 1 over 2 pi minus infinity to plus infinity to the power ikx dk is a faithful representation. And in order to prove this, there is another property. So for any well-behaved function fx, by multiplying with this sum delta x minus a, that must gives you a fa, that must gives you fa. For this representation, you can check this for your completeness. So it can also be written in a very compact or in a very general manner. Delta x minus a, that is equals to delta a, or delta a minus x is a symmetric, and 1 over 2 pi minus infinity to plus infinity e to the power plus minus ik x minus a dk. This is a general representation of Dirac-Delta function in this way for any real number a, and result is true for both the signs in the integrand. Another way of looking at it, from the Fourier transform we know fx equals to 1 over 2 pi minus infinity to plus infinity fk e to the power ikx dk, and fk equals to 1 over 2 pi minus infinity to plus infinity fk e to the power minus ikx dx. This is a Fourier transform pair, and I put this thing here fk, and what happens to that? Fx equals to 1 over root 2 pi minus infinity to plus infinity. I put it here. That means I am 1 over 2 pi root 2 pi 1 over 2 pi minus infinity plus infinity. I am changing the variable. It's some variable y fy e to the power minus iky dy, and whole thing there is a minus ikx dk. It is clear, I think. And then it minus infinity to plus infinity. Fy is sufficiently well behaved in this case and exchange the order of integration. So therefore I am writing in this way 1 over 2 pi minus infinity to plus infinity ikx minus iky, that is ikx minus y dk, and multiplied by fy dy. As we know, fy is sufficiently well behaved. So, and it is basically the representation of Dirac-Delta function delta x minus y. So therefore we can say delta x minus y fy dy. It can be. So this is we already familiar. This is a representation of the Dirac-Delta function, where delta x is nothing but delta x minus y, rather 1 over 2 pi minus infinity to plus infinity I k x minus y dk. That is well known to us. And find the Fourier transform. This is a home task, or rather I have done it already. Fk equals to 1 over root 2 pi delta x e to the power I k x dx. What will be that? Basically 1 over 2 pi. That means a constant. That is a constant. That means the Fourier transform of a constant, basically. And find the Fourier transform of delta x minus a. Fk equals to 1 over root 2 pi minus infinity to plus infinity delta x minus a e to the power I k x dx. It gives you x equals to a. That means e to the power I k root over 2 pi.